Okay, so now that we have talked about why we need to use FutureTask to implement a Memoizer, let's talk about how to implement a Memoizer using FutureTask. And this is a really interesting discussion. Same semantics as before, just a different implementation. And as you'll see, it's a more complicated implementation, and that's because ConcurrentHashMap in Java 8 and beyond absorbs all this complexity into a single method called computeIfAbsent, which is why they put it in there so you wouldn't have to do this yourself. So here's what it looks like. We have Memoizer, which is a class that implements function. So we can plug and play this as we did before. Here we're going to go ahead and have a ConcurrentHashMap. And let's assume, for sake of argument, this is a Java 7 ConcurrentHashMap. And I've also sort of hard-coded the hash map here. In the previous version of Memoizer, I used it as a parameter you could pass in, but that was overkill. This is just showing how to do it if you have a Java 7 or Java 5 ConcurrentHashMap. Now, before the ConcurrentHashMap was, concurrent map KV for the version that used Java 8 ConcurrentHashMap semantics. Now that we're using the previous versions of Java ConcurrentHashMap, we're going to have a different value. And the value is going to be a future to a V. And this is going to be used to ensure that the expensive function is only called once, no matter how many threads all come in and try to do this at the same time on the same key. Here is the function, which is stashed away by the constructor. So the constructor stashes the function as a field. Notice we don't parameterize the hash map. We just parameterize the function. Let's take a look at the apply method. This is where the magic happens. And this is really very, very subtle code. It's very cool code, but it's very subtle code. So apply is, of course, the method signature we inherit from function. So apply is what's going to go ahead and ensure that the computation only runs once, and it's going to do the computation and return the value if it's going to store the value if it's not already there and return the value no matter what. So the first thing we do is we come in here and we use the older version of Java ConcurrentHashMap to see if there is already a value associated with a given key. So the key is passed in as a parameter. We go and we call get, which efficiently goes and looks up and says, hey, is this key associated with an existing value in the ConcurrentHashMap? And we get back a result. Now, again, keep in mind, this is the earlier versions of ConcurrentHashMap. What will happen in this case is it'll return a future, and if this is the first time we've gone to check to see whether or not there's a value associated with the key, if this is the first time in, then we're going to get back a null, because the values in a hash map are all preset to null. So if you try to get a value that is not yet associated with a key, you'll get back a null. So that's how you know it's not there. So if the future is null, then we're going to go ahead and compute the value that's associated with that key. And we'll see how that works in a second. That's the magic. And the thing to remember about this is there could be multiple threads that would simultaneously come in to apply at exactly the same time for exactly the same key, and multiple of those threads could all find the value to be null, because they all came in at the same time. They all get a null value. So there could be multiple threads that would have this condition succeed where future equal null. So remember that. There could be multiple threads that will find that, and therefore multiple threads could call compute value. We'll talk about compute value in a second. That's the key heavy lifting method here. And then there's also another call called get future value. And this is going to return the value of the future, but it's going to block until the future is actually computed. And you'll see how that's going to work. And what's interesting here is the first thread that comes in here at a simultaneous time will not block. It'll actually do the computation. But all the other threads that come through will end up blocking on the future in this call until the compute value computation is done by the first thread that came in. So this is basically implementing that cool atomic check then act feature that ComputeIfAbsent had out of the box in Java 8 and beyond, and we're doing it using FutureTasks. Okay, so let's go look at compute value. This is where all the magic happens. This is complicated. So compute value will compute the value associated with the key and return a future task that's associated with it, which is a future. And here's what it does. The first thing it does is it makes a new future task. Now keep in mind, multiple threads could all be calling this thing simultaneously. So multiple threads could come in here and all be calling this code. And what this code does is it makes a future task, and it gives it a lambda expression, which will go ahead and apply the function, which is what we stashed away in the constructor, on the given key. Remember, this is being called because we don't have a value yet associated with that key. And so that's going to go ahead and call this method. Now, keep in mind, this method doesn't actually run at this point. This just gives it the code to be run down here. So it's saying, when we call the run method on the future task, this is what the call method will do. This is the lambda expression that corresponds to the callable lambda that's being passed in here. So when run is called down here, it'll invoke this callable lambda to compute the value and store it in the cache. We then go ahead, after we create this future task, and we call mcache put if absent. Now, put if absent has been around since the concurrent hash map first came out. Compute if absent was added later. So put if absent is a perfectly valid, non-modern legacy Java method on concurrent hash map. And what that does is that will atomically try to add the future task to the cache as the value that's associated with the key. And so what it's going to do, put if absent will, as the name implies, atomically add this value one time if, in fact, it isn't already there. So it puts it in the hash map if it's not there. And because it's an atomic operation, only one thread will succeed in doing this. And what will happen is whichever thread comes through here, let's say 4 threads come in at the same time, only one of them will succeed in putting the future task in. And the first thread that puts the future task in, this is really important to understand, will return a null future because it was the first time in, and so the previous value was null. All the other threads that come in after the value is added will all find that the value for the key is non-null. And that's because the first thread in put it in there. And so it'll get back a null, and all the other threads will get back non-null. This is really subtle. So keep in mind that only one thread will actually have a null as the return value for put if absent. So the first time in, the first thread to make this assignment work will get a null. All the other threads will get non-null. So we then come in here and we check. We say, hey, is this thing null or not? And if it is null, we were the first thread to successfully add the future task into that element in the hash map under that key. So the future task has now been added as the value for that particular key. So that means we're the first one in, and the value has not yet been computed because we just added it. So in that case, then, we go ahead and we call run, and run will go ahead and apply this particular call, which will go ahead and, in this particular case, do the computation, and it'll store the results in the cache when the computation is finished. So this method will be called only one time by the first thread in, and after it's done, it's going to go ahead and return the future task. So run will forward to call, which in turn forwards to mfunction apply key. So this is the lambda callable, which is playing the role of the call method. When that call method is called, that's the computation that gets run. And so that'll go ahead and do the computation. And then we return a future to the task that just completed. And if future is not null, in other words, if this condition failed, then the value is already in the cache. So we'll just return it. But keep in mind that what we're returning here is a future that has not yet been completed. It's just a future to something that is possibly still doing some long-running computation. So here then is the get future value method, which returns the value of the future blocking until it's completed. And you can see what it does here is it calls get on the future. So the first time in thread, that guy won't block when it calls get because it will have already gone ahead and run the computation, which will made the future be finished at that point. So the value will have been computed. But any other threads that get here while the long-running computation is taking place are all going to block on this future. And so they're not going to be able to make forward progress until this run method completes. So super duper duper cool. The point of this, however, is that this is also subtle, complicated logic. And that's why they took this out of the hands of developers like us, who had to follow a recipe, a pattern that I just walked through here, and stuck it into ConcurrentHashMap via the compute if absent method, which made it a lot cleaner and made it so you don't have to think too hard about how this is going to work.